Okay, let's continue on to the next page. Graphs of polynomial functions. Beginning with end behavior of polynomial functions. If the degree is even and the leading coefficient is positive, then f of x approaches positive infinity as x approaches negative infinity, and f of x approaches positive infinity as x approaches positive infinity. This is just a technical way to describe how x and y interact. F of x, of course, represents the y. X represents itself. So as the y values get larger, the x values get smaller. And as the y values get larger, the x values get larger. As x goes to the left, y gets bigger. As x goes to the right, y gets bigger. This is true for every even function that has a positive leading coefficient. If the degree is even and the leading coefficient is negative, let's highlight that, then f of x approaches negative infinity as x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. If the degree is odd and the leading coefficient is positive, then f of x approaches negative infinity as x approaches negative infinity, and f of x approaches positive infinity as x approaches positive infinity. If the degree is odd and the leading coefficient is negative, then f of x approaches positive infinity as x approaches negative infinity, f of x approaches negative infinity as x approaches negative infinity. Actually, that's a positive. And that's how that particular sequence works. We're going to take a look at graphs to help us better understand these types of relationships. The real zeros of a polynomial function. The maximum number of zeros of a polynomial function is equal to the degree of the polynomial. A zero of a function is a point at which the graph intersects the x-axis. On a graph, count the number of real zeros of the function by counting the number of times the graph crosses or touches the x-axis. And again, we're going to be taking a look at graphs where we can see the exact zeros. Let's move on to this example. Determine whether the graph represents an odd degree polynomial or an even degree polynomial. Then state the number of real zeros. So as we can see, this curve from left to right starts to move up, dips down, back up again, down, and then up as it finishes its end behavior. And that's really what we're referring to when we look at end behavior. It's where the graph finishes in both directions. Okay, so up and to the right, down and to the left. As x approaches negative infinity, f of x approaches negative infinity. In other words, as x goes to the left, again, f of x pertaining to y suggests that y is going down or is decreasing. That's technically how the negative infinity relates here. And decreasing, you can see, in other words, the y values are going down as x goes to the left. So x goes left, y goes down. That's the easier way to remember that. As x goes to positive infinity, f of x goes to positive infinity. So as you can see graphically, as x goes to the right, your y values finish or end going up. So let's go ahead and write that as x goes right, y increases. Okay. So it is technically an odd degree polynomial function. The graph intersects the x-axis at one point, so the function has one real zero. Okay. Let's highlight odd degree. All odd degree functions are going to be down and to the left and then up and to the right, or vice versa. Up and to the left or down and to the right. So those are the two types of odd degree functions, at least the end behavior. Back to the intersection of the graph with the x-axis. Let's go ahead and highlight that particular value. Looks like it's not quite at -3, so we'll say -2.6 something. Okay, because we don't know the actual equation of this particular graph, we're not going to be able to easily define that value, but at least we can pinpoint on the graph the value in between. Looks like -2 and -3. Okay. So, the exercises. For each graph, part A says describe the end behavior. Part B, determine whether it represents an odd or an even degree function. And then part C, state the number of real zeros. Okay. So, with problem number 1, you can see the graph goes up and to the left, goes down, up, down, and then back up again, up and to the right. Any time that you see the end behavior of a function has its 2 arrows pointing up or 2 arrows pointing down, as we see in number 2, this is technically then an even degree function. So we can say that right away. Okay. As far as the end behavior of this particular function, well, the end behavior, because it's an even degree, and because we can really just see where the arrows are pointing, we can say as x goes to the left, in other words, -infinity, f of x, look at the graph, as x goes left, y goes up, or positive infinity. And as x goes to the right, or positive infinity, f of x, as you can see, x goes to the right, f of x or y goes up, so positive infinity. So that's the end behavior, but also the degree. So I've answered really parts A and B, as you can see. Part C, state the number of real zeros. So we are just going to maybe just plot points where we see it crossing the x-axis. There's 1, 2, 3, 4, 5, and 6. Now here's the neat thing about finding those zeros just by looking at the graph. The fact that there are 6 zeros equates to the fact, or relates to the fact, that it is an even degree function, and 6, of course, is an even number. So that particular example is an even degree with that end behavior, 6 zeros, even number there. But also, I'm going to put a little plus sign. The reason it's a plus as opposed to a minus, well, the graph opens up as opposed to opening down. Maybe that'll be a good segue for number 2. So as we look at number 2, I'm going to answer, like I did on the last problem, I'm going to answer whether this is even or odd first. So we can see here that we've got 2 arrows pointing down. Right away, that speaks to this being an even degree. Okay. Furthermore, because it opens down and not up, the 2 arrows point down in this instance, we're going to indicate a negative even degree. So as far as positive versus even, we're looking at the leading coefficient of the actual function, which in this case we don't know, but we can at least say positive in this instance, negative in this one. We can jump to the end behavior as we look at the graph. As x goes to the left, or -infinity, f of x or y goes down, so -infinity. And then as x goes to the right, in other words positive infinity, you can see the y values again going down. So f of x approaches -infinity. As far as the real zeros, well, looks like there's only 1 there. Now here's the deal. That 1, 0 doesn't technically match with the fact that it's an even degree function. So technically what we do then is refer to this as a repeated zero. All even degree functions have to have the number of zeros that match it. In other words, 1, because it's not even, well, it wouldn't technically correlate with our definition. So what we say is that 1 0 is repeated at that value. And we're going to talk more about why repeated zeros are important and how they differ from just any old zero. But that's that with that problem. Let's move on to number 3. So in problem number 3, we can see that our end behavior up and to the left, down and to the right. So hopefully, as we relate back to the very first exercise up at the top here, we can identify this right away as an odd degree. Okay. Again, if it opens up and to the left, down and to the right, or down and to the left, up and to the right, it's technically odd. End behavior as x goes to positive infinity. Actually, let's start with negative. As x approaches negative infinity, or to the left, in other words, the y values are increasing. Positive infinity, therefore. As x goes to the right, your y values, x approaches positive infinity, that is, your y values go down. Okay, now it does appear that our curve may do some kind of upward swing, but we don't know definitively. As x goes to positive infinity, therefore we're going to say that it is going to just continue to go down to negative, because we don't know if it goes up officially or just continues to swoop down. Even though it kind of makes that turn, we don't know for sure. Okay, let's go ahead and identify the values here, here, and here. Okay, so we're not going to go ahead and specifically pinpoint the ordered pairs, but we are going to say that there are 3 zeros. So I'll write that here. And yes, 3 is an odd number, so it does match with the type of function. This is an odd degree function. And then last but not least, we do need to identify whether it's positive or negative. Just as a finishing touch here, it does appear, because it's up and to the left, down and to the right, if we go back up to our definition, the very top, we pinpoint odd and odd, positive and negative. As x goes to negative, f of x goes to negative. So as x goes left, f of x goes down. As x goes to the right, f of x goes up. Okay, so it doesn't appear that our graph is doing that. As a matter of fact, it's not. It's doing this. As x goes left, f of x goes up. As x goes right, f of x goes down. So that technically speaks to our graph. Yes, this is therefore a negative odd function. So we'll put a negative here, and there we go. So that concludes this lesson.